So the next we will see, and in 1924, another things came into existence. In 1924, de Broglie gave the hypothesis, and he said that, the electron is not a wave, it can behave like a wave also. And what he did, he unified the by that time two established equations, E is equal to h nu and E is equal to mc square. And he actually extended the idea of what did Planck tell? Planck in 1905 said that energy is not only quantized while it is being absorbed or emitted, but even during the transmission it is transmitted in energy packets called photons. And in fact this idea of photons revived the theory of corpuscular nature of light, which was given by Newton. So you know that initially about the nature of light, corpuscular theory was given by Newton. Then again wave nature came into existence because light diffraction and interference and diffraction and polarization were known. Then there's an ethereal concept of ethereal medium came into existence, and it was said that no, electromagnetic radiation is a wave, it is not particle. But in 1905, when Planck gave his theory for the photoelectric effect, he extended the idea of quantization to transmission of electromagnetic radiation also in terms of energy packets, and he said that electromagnetic radiation travels in energy packets called photons. So that was actually revival of the Newton's corpuscular theory. So first particle, then wave, then again particle, and looking at this, de Broglie said that okay, everything in this universe can have a wave nature also and can have a particle nature also, and it will depend upon which will predominate will be decided by the mass. So he equated the two equations, E is equal to mc square and E is equal to h nu, and he gave that lambda wavelength of the matter will be inversely proportional to the mass. Lower the mass, higher will be the wavelength, and you cannot neglect it because h is a constant, c is a constant, c of the velocity of electromagnetic radiation. So higher the mass, lower will be the wavelength. You can neglect it, it will behave like a particle. If the mass is lower, then wavelength is quite high and you cannot neglect it. So this came into this concept, this hypothesis was proposed by de Broglie in 1924. Okay. And we can put this equation in different forms. So since kinetic energy is 1 by 2 mva square, so you can put it mv you can put as h divided by 2m into kinetic energy. So this you can do. Okay. And to quantitatively just give you an idea that if you look at the 1 kg of mass moving with a velocity of 10 meter per second, then its wavelength is 6.6 into 10 to the minus 25 angstrom. It's very, very low wavelength because the mass is very high, it's 1 kg. Okay. And the velocity is 10 meter per second. In contrast to this, if you have an electron, so then the electron mass is 9.1 into 10 to the minus 31 kg. So compare this with this one. Okay. And if it has an energy in terms of kinetic energy also, I have given you an equation that you can check yourself that whether this value you get it or not. The equations are there. You can put these values, kinetic energy values, and then mass value and h value, and you can find out the lambda value. So lambda you obtain is 1.2 angstrom. Compare this lambda with this lambda, 10 to the minus 25 and 1.2 angstrom. So this is quite appreciable wavelength, and this cannot be neglected. So for very small particles, say for example electrons, protons, molecules, it's a complete neglect of when I say molecules, very small molecules, then you cannot neglect the value of wavelength. So wave nature and particle nature both exist, dual nature exists for subatomic particles. So this was proposed by initially by de Broglie, and later on electron diffraction were observed by Davison and Germer, and so it was experimentally also confirmed by Davison and Germer and J.P. Thomson in 1927. Okay. So diffraction and pattern of the beam were observed. So this was another landmark development in the development of the quantum mechanics. Okay. Then another development took place since it is a wave. Now wave was already known to physics people. A standing wave was known to people. So what happens to the standing wave equation, to the de Broglie wave? If it's a wave which has a wavelength, we can say the de Broglie wave of electron with a mass of 9.1 to 10 to the minus 31 kg and an energy of 100 electron volt is 1.2 angstrom. So what will happen to the generalized standing wave equation if we talk about the de Broglie wave? So now let's look at that picture. So this is a standing wave. What happens that you have two ends, two walls, and in between the two walls a string is stretched. So suppose this is a x-axis along which you tie the string with in between two walls, and then you pull that string downward in the y direction. What will happen? A wave will be created, and that wave will be created from both sides, and it will result into several nodes. Okay, and this is called a standing wave. So the particles or the components of the string move along y direction, up and down. So there is an upward force and downward force both taking place. If you look at this force, upward and downward force along a very small stretch of the string, and you apply the Newton's equation of motion, then you get the equation for a standing wave, which we will not derive, but it's already available. Those from physics normally do. So what we are doing, we are disturbing the string in the y direction. So if you want to know that how the components of the string will move along x direction, along x-axis, and the disturbance is along the y direction, then the movement of any component of the string will be subject to two factors. Another, where you are measuring and at what time you are measuring. So you have two variables here to measure this y is the disturbance. So two variables to measure, another is x, another is t. Okay, look at this particular portion of the lecture is very important for the initial quantum mechanics which we will be doing. Okay, so understand it very properly. Now what we say that, okay, since we have two variables, so let us separate this variable into two components. One is fx, which is only x dependent, another is phi t, which is time dependent. Okay, and then I have written that the total function y xt is a product of fx and phi t. This is very common throughout the quantum mechanics, that if whenever you have a function, a wave function which depends on more than one variable, then you can split this wave function into component functions, each depending on only one variable, and then you can write the total wave function as the product of these wave functions. In contrast to this, if the energy is dependent on several variables, then energy also you can split into different different component, each depending on only one variable, but the total energy will be sum of the energies of the components. Okay, so this is the common course which we will doing. I will talk about later on in the postulates of quantum mechanics also the details, but this is what we have done here, that fx is a part of the wave function which is x dependent, and phi t is the part of the wave function which is time dependent. So the total function is y xt is equal to fx into phi t. Okay. Now I said you that if you are disturbing this string, then you can calculate the forces on a small stretch dx or something like that, and there will be gradually an upward motion and downward motion in a periodic movement of the string. So if you apply those rules, then you can find out the equation for a standing wave, and that equation for a standing wave is known. This becomes equal to this one. This gives you the displacement. d square y xt divided by dx square is equal to 1 by c square, where c square is the velocity. It could be for any velocity. Don't confuse with the c square velocity of electromagnetic radiation only. So instead of c, you can replace it by v also, v square, any wave. Okay. So now if you put these values fx phi t into this equation, then you get this one. Now since you on the left hand side you are double differentiating with respect to x, so phi t component will be constant, and on the right hand side you are differentiating with respect to t, so phi fx component will be constant, so you can separate it. Phi t d square fx by dx square, and then fx divided by c square d square phi t divided by dt square. Okay. Now it's the same equation, fx square d square phi t divided by dt square. Okay. Now we can put this equal to a constant minus omega square. Okay. So since this also is minus omega square and this also is minus omega square, so you can put, first take the x component of function, so c square fx is d square fx divided by dx square minus omega square, and if you rearrange you get d square fx by dx square plus omega square fx divided by c square. Equation number 3. And then in the next part you can do 1 over phi t d square phi t divided by dt square minus omega square, and this gives you this equation. Look at this equation 3 and equation 4. This is x dependent and this is time dependent. So what we did is, we were having only one equation, d square y by dx square. Look at this one, d square y divided by dx square 1 by c square d square y divided by dt square. But we were knowing that we have two different variables x and t. So using this equation that yxt is fx into phi t and splitting that function into two components, we got two different equations, each depending on only one variable. And this is called separation of variable, which again we will be doing time and again during the course of during this course. Okay. So this, what we did is called separation of variables. Okay. So we did the separation of variables. Then in the next, we take the common solution, that is time dependent equation, and time dependent equation is d square phi t divided by theta square omega square phi t, and this double differential equation can have many different solutions, several different solutions, and one of the possible solution I have written is phi t is equal to a sin omega t plus b cos omega t. That you can check that d phi over dt, you first find out, it will be how much? It will be a omega cos omega t, cos will be minus b omega sin omega t, and then you double differentiate, it will be minus omega square sin omega t, and again sin is cos omega square cos omega t. Okay, and so what you can do, minus omega square you can take common, and then you have a sin omega t cos omega t, and this is what? This is your phi t. So this is equal to minus omega square phi t. So if you differentiate this solution, you get back the equation number 5. So this is one of the possible solution of the time dependent equation, where a and b are constants. Now these constants we will determine later on from the boundary condition. I will tell you. This omega is called now circular frequency, and this omega is given as 2 pi nu, or so 2 pi c divided by lambda. If you use this value of omega, then your x dependent equation becomes d square fx by dx square 4 pi square by lambda square. See, this was omega square fx divided by c square. So omega square fx is there, okay. Omega square becomes equal to 4 pi square c square by lambda square, okay. So c square will go, and now it will be 4 pi square by lambda square. So fx equation using this part gets converted to this one. Since you have written the solution for the time dependent equation, so you can write the solution for x dependent equation also very easily. The only thing is this, that here instead of omega square, you have written omega t. So instead of 4 pi square by lambda square, you will write 2 pi by lambda, okay. And the two constants you have to use, we used a and b there, and now in the next I have used p and q. So p sine 2 pi divided by lambda x, q cos 2 pi divided by lambda x. Since the form of the equation is same, so again what you can do, you do it dfx by dx, you find out what is this, and then you find out d square fx by dx square, you find out these two, and using this one p sine means fx, you will be with fx is equal to this one whole equation, okay. And you will find that you get back the equation number 7 if you differentiate that you do it yourself, okay. So one of the solution of x dependent equation is fx is equal to p sine 2 pi divided by lambda x and q cos 2 pi divided by lambda into x, okay, where p and q are constant, of course, okay. So now once you have this solution, what will be the value of x component of the function, which is fx, if you apply the boundary condition? What was the boundary condition? You have two walls and a string is attached to the two walls, okay. If you start with the first wall and you give a value 0 to this one, then the second wall will have a value of a. So that your length in the x direction is 0 to a. So at the wall there will be no wave, and so the function should be 0. So the first boundary is that at x is equal to 0, fx is 0. At x is equal to 0, fx is 0. And if you put this value x is equal to 0, then you have q cos 0 and p sin 0. So sin 0 will be 0 and p, the first term will be 0, this term will be 0. But cos 0 is 1, so q will remain there, and fx is already 0. What does it means? It means q is equal to 0. And if you want to write, I will write fx is equal to 0 equal to p sine 2 pi by lambda into 0 plus q cos 2 pi by lambda into 0. So this is q cos 0, this is p sin 0. So this becomes 0, so q is equal to 0. It's very easy, okay. Next, the next boundary condition is that at other wall, when the distance is a, it will also the function is 0. So if one of the q is 0, so your equation 8 reduces to this one. Equation 8 reduces to this one, q is equal to 0, one part goes. And now if at x is equal to a, fx is equal to 0, so you can write this equation as fx is 0 is equal to p sine 2 pi divided by lambda into a. Sorry. X is a now. So this is the second boundary condition. Now for this equation to be valid, either this is 0 or this is 0. If Q was already 0 with the first boundary condition, if you put P also 0, then the whole function becomes redundant. Fx, you do not have anything. Okay. So we say that no, this sine 2 pi lambda, 2 pi a divided by lambda is 0. This is equal to 0. And you know that sine 0, we have the 0 value for sine n pi also. So it becomes 2 pi by, so from this equation you can write 2 pi by a lambda into a is equal to n pi, or 1 by lambda you can find is n divided by 2a. And if you put this value in the fx equation, then you have, with the boundary condition, you have this equation. Fx is equal to p sine n pi x divided by a. Okay. Till now, we did not talk about anything de Broglie wave. I started talking about that what happens to the de Broglie wave if we talk about the standing wave equation. Okay. So how does the standing wave equation changes for the de Broglie wave? Now you see, we will use the de Broglie hypothesis. De Broglie said this one, lambda is equal to h by mc. Okay. Kinetic energy we can write as energy is equal to 1 by 2 mc square plus v. Total energy is kinetic energy plus potential energy. So this is kinetic energy, this is your potential energy, and this we can further m square c square divided by 2m into v. And since m square c square is equal to, if you write mc is equal to h divided by lambda, so m square c square is h square by lambda square. So you can write this one. And if you use this one, your equation changes to 2m e minus v h square is equal to 1 by lambda square. We can use this equation and put this value 1 by lambda square from here into this equation. d square by into equation number this one 7. Equation number 7. 1 by lambda square value if you put in equation number 7, what you get is d square fx by dx square plus 8 pi square m h square e minus v fx is equal to 0. So this becomes the one part is x component part of the wave function from the standing wave. We will be mostly talking about the time independent quantum mechanics. So the time independent part of the standing wave equation now is d square fx by dx square 8 pi square m by h square e minus v fx is equal to 0. All of you in your undergraduate courses or even in your plus 2 level courses have done this equation. This equation is called Schrodinger wave equation in one dimension. Okay. So Schrodinger wave equation is nothing but it is a standing wave equation for a de Broglie wave. That's all. Okay. So there are different forms for the Schrodinger wave equation. We have done it for one dimension. Schrodinger wave equation in one dimension. We have done it. We can write it for the 3 dimensional also. So this is for the 3 dimensional. For 3 dimensional, this equation we can write. Okay. And then again you can rearrange, you can add Laplacian operator here, and then with Laplacian operator this is the equation, and then you can rearrange this equation to give you a Hamiltonian also. This is your Hamiltonian. If when you multiply by minus h square divided by 8 pi square m, you get this equation, and finally you get the Hamiltonian, and with this Hamiltonian you write this part, h psi is equal to e psi, where this psi is x, y and z dependent psi. So the shortest possible form of the Schrodinger wave equation is h psi is equal to e psi. This is one of the form. This is your one dimensional form. So whenever you have to deal with the one dimensional problem, you will use this equation. When you have to deal with the 3 dimensional problems, you can use this equation or this equation, 3 dimensional problem, and this is also use. So the shortest form of the Schrodinger wave equation is this one. Okay. So for now, I will stop, and in the next class, another important development took place. This came into being around 1926, 25-26. Schrodinger equation was given, and in the next 2-3 years, Schrodinger did many problems of quantum mechanics and published it. Okay. So that we will talk about later on, those problems. But another important thing came into existence in 1927 when Heisenberg gave his uncertainty principle. That we will talk about in the next class. Okay, thank you.